Stroke risk estimation using viscoplastic energy method. VMT, of physics and topological data analysis, TDA, of mathematics, number 1377, VMT sharp 717, TDA sharp 001, October 4, 2025. Gerald C. EclaireMD Foundation. Category, Neuroscience, and Computational Medicine. Mission statement. I write these medical papers not for fame or recognition, since I have already lived a long and successful life, though not always a healthy one. My purpose now is to share what I have learned about health, disease, and medicine, so that others can better understand their own conditions, prevent illness, and live longer, healthier lives. Preface. 58 years ago, when I was 20 years old and in my senior year of college, I was introduced to a course titled Topology. At that time, I did not fully comprehend its potential applications beyond the theoretical framework of mathematics. My subsequent graduate studies focused on various engineering disciplines, emphasizing practical and analytical problem solving through mathematical modeling and physical principles. However, after dedicating the past 16 years to medical research, including the publication of more than 700 papers utilizing the viscoplastic energy method, I have recently revisited the concept of topology and begun to contemplate its relevance to biomedical science. In medicine, topographical concepts and methods have primarily been applied in the field of medical imaging. However, I am particularly intrigued by the potential to extend the mathematical principles of geometry, shape, and connectivity to investigate complex structures and interactions within diseases and physiological systems, thereby uncovering new dimensions of biomedical understanding. Today, I have decided to explore the application of topology to analyze stroke risk in relation to three key variables: biological age as a representation of the aging process, systolic blood pressure, SBP, as an indicator of hypertension, and estimated average glucose, EAG, as a marker of diabetes severity, as described in my paper number 1376. I was first exposed to topology about 60 years ago. Although topology has existed in mathematics for more than a century, its biomedical applications beyond imaging only began to emerge around the mid-2010s, with the rise of data-driven systems biology. Even then, most studies were fragmented, and few, if any, applied topology systematically to a personalized, longitudinal, pathophysiological dataset such as mine. This paper is very likely the first comprehensive application of topological data analysis, TDA, to a non-imaging, non-genomic, longitudinal human health dataset, validated by both a physics-based viscoplastic energy model and 16 years of real clinical evidence. Significant statement. This study pioneers the use of topological data analysis, TDA, beyond medical imaging, applying it to longitudinal pathophysiological data for the first time. By integrating TDA with the physics-based Viscoplastic Medicine Theory, energy model, VMT, it introduces a unified framework, linking geometry and energy in human health. This interdisciplinary approach opens a new pathway for personalized systems medicine. Introduction. Stroke is one of the major causes of death and disability worldwide. The Framingham Stroke Risk Profile, FSRP, provides a 10-year probability of stroke, and has long been a standard in clinical practice. However, its structure is dominated by age, which makes it useful for populations but less responsive to lifestyle change in individuals. To gain a more dynamic and personalized view, I developed the Viscoplastic Medicine Theory, VMT. The VMT energy model measures how biological stress and strain interact over time, similar to how materials deform under load. In this study, I added another mathematical method, called Topological Data Analysis, TDA, which analyzes the shape and structure of data rather than only numerical values. The goal was to compare the physical energy dynamics of VMT with the geometric structure of TDA, using my 16 years of personal longitudinal data from 2010 to 2025. Method. I used three key input variables: real age, systolic blood pressure, SBP, and estimated average glucose, EAG. The output variable was my VMT-based stroke risk index, representing vascular strain, i.e., blood vessel damage. All three input variables were normalized with the following factors: age, divided by 70, SBP divided by 140, EAG divided by 120. For the TDA analysis, I calculated the Euclidean distance between each pair of years, to quantify how far one annual data point was from another within a three-dimensional space, where the x-axis represents age, the y-axis represents systolic blood pressure, SBP, and the z-axis represents estimated average glucose, EAG. I then applied a Vietoris-Rips complex and calculated zero-dimensional persistent homology, which tells how many clusters or connected components exist, and how they merge as the distance threshold increases. For the VMT analysis, I used my existing stroke risk energy calculations that quantify stress-strain, interaction and cumulative vascular damage based on the same variables. TDA results. The TDA analysis revealed one major connected cluster, which means that all 16 years of data belong to the same health phase overall. The maximum persistence of 0.38 indicated that only one structural transition occurred across the entire 16-year period. From 2010 to 2012, the average pairwise distance among data points was 0.34, showing wide separation and instability among the three input variables. After 2013, this distance decreased steadily, reaching 0.09 by 2025. This contraction means that my physiological system became more stable and homogeneous over time. The period from 2010 to 2012 showed the highest local curvature in the manifold, which corresponds exactly to the period of my highest blood pressure and glucose levels. From 2013 to 2015, the manifold tightened rapidly, and from 2015 onward, it became compact and spherical. In simple terms, the shape of my health data changed from a stretched, unstable geometry into a smooth, stable one. VMT and TDA comparison. Both the VMT dynamic energy model and the TDA structural shape analysis describe the same health journey from different perspectives. One from the viewpoint of physics and the other from the perspective of mathematics. In the VMT model, stroke energy started at 3,945 units in 2012, and dropped below 100 units after 2015. This shows a 97% reduction in cerebrovascular stress energy. The TDA model, on the other hand, shows that the geometry of my health data contracted by about 73% over the same time period. Both models identify from 2010 to 2012 as the period of instability and 2015 as the turning point toward equilibrium. The VMT model quantifies the degree of deformation or internal stress occurring within the cerebral vascular system, while the TDA model reveals how the relationships among key variables, age, blood pressure, and glucose, evolve toward greater coherence. The VMT curve measures changes in energy amplitude, whereas the TDA manifold characterizes the continuity of geometric shape. Despite their different analytical foundations, the two methods produce highly consistent results. A 97% reduction in VMT energy versus a 73% reduction in TDA structural variation, thereby confirming the reliability and mutual validity of both approaches. Detailed year-by-year observations. From 2010 to 2025, the Framingham Light Stroke Index ranged from 139 down to 94, while my VMT Stroke Index ranged from 158 down to 91. The average value of the Framingham Light Index was 99.3, while the average value of the VMT Index was 101.3. The correlation between the two was 0.995, or 99.5%. This means that the two curves followed almost identical patterns. Although the VMT values were slightly higher in early years when my diabetes was uncontrolled, my hemoglobin A1C was at 12%. Both curves show a steep decline from 2010 to 2012, a steady stabilization from 2015 to 2020, and a near flat shape afterward. This pattern mirrors my own clinical history, where lifestyle modification without medications chemical intervention began in 2010, with major improvements observed after 2013. VMT energy contribution analysis. The VMT energy contribution ratios were as follows. Age contribution is 26%, SBP contribution is 34%, T2D contribution is 40%. This indicates that the primary forces behind my stroke-related stress load were type 2 diabetes, T2D, as the dominant factor, followed by systolic blood pressure, while biological age played the smallest role. Diabetes served as the chronic, underlying corruptor that gradually weakened my blood vessels over time, whereas blood pressure acted as the acute trigger capable of causing vascular rupture. This pattern aligns precisely with my actual medical event of hemorrhagic stroke on June 21, 2025, when an acute hypertensive episode reaching 175 mm of mercury led to a stroke after decades of cumulative metabolic damage from diabetes. Discussion. My Topological Data Analysis, TDA, and Viscoplastic Medicine Theory, VMT, models complement each other in describing the same 16-year, stroke-related health journey from 2010 to 2025. From 2010 to 2012, my blood pressure reached 180 mm of mercury and EAG exceeded 270 mg per deciliter, producing a chaotic and irregular health pattern. The TDA manifold was widely scattered, and my VMT curve showed extremely high stroke-related energy values, 158, 102, indicating instability. From 2013 to 2015, the manifold contracted as the relationships among H, SBP, and E/G became more coherent. This corresponded with a sharp VMT energy drop and marked clinical improvement. After 2015, the geometry became nearly spherical, and the VMT energy stabilized below 100, signifying low internal stress and high systemic resilience. The 3D TDA scatter diagram converts my 16-year data into a geometric shape, with each point representing 1 year's normalized values of age 70, SBP 140, and E/G 120. The orange points, from 2010 to 2012, mark the chaotic phase. The middle points, from 2013 to 2015, represent recovery, and the blue cluster, from 2016 to 2025, indicates long-term equilibrium. This contraction of points over time visually confirms my physiological stabilization. The combined graphic figures clearly illustrate this health transition. The upper panel, TDA, shows how my health geometry evolved, from an irregular network to a smooth, circular shape after 2015. The lower panel, VMT, presents the real stroke risk energy curve, dropping from 158 to approximately 91 and remaining steady thereafter. Together, they show that reducing metabolic stress energy leads to structural coherence and systemic harmony. VMT quantifies the magnitude of internal stress, while TDA reveals the shape of systemic organization. Despite their different scientific foundations, physics versus geometry, they capture the same process: chaos, recovery, and stability. The VMT curve measures how much stress energy is released. The TDA manifold shows how the body reorganizes as recovery unfolds. Conclusion: this 16-year longitudinal study demonstrates that VMT and TDA together describe the same biomedical reality. VMT measures dynamic energy dissipation, TDA visualizes structural order. Both reveal that from 2010 to 2012 were years of metabolic disorder, from 2013 to 2015, a recovery phase, and from 2016 to 2025 a stable equilibrium. Unlike the Framingham model, which mainly reflects age, these two methods, VMT and TDA, respond to real-time physiological changes and show that stroke risk can be reduced through disciplined lifestyle management. The human body behaves both as a dynamic energy system and a geometric structure, capable of transforming from chaos to stability through measurable self-reorganization. Plain English summary: my VMT energy curve shows how much stress was inside my vascular system. My TDA diagram shows how the geometric shape of my health data changed over time. Both reveal the same truth: my body moved from chaos, from 2010 to 2012, to stability after 2015. This confirms that lifestyle management can reshape health, lowering internal energy stress and restoring systemic balance. Disclaimer: this content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article, and its related materials belong to the author, Gerald C. Appendix: TDA data and derived metrics, from 2010 to 2025. This appendix summarizes the topological data analysis. TDA, results derived from my 16-year longitudinal stroke dataset, covering the years from 2010 to 2025. The three key input variables were real age, systolic blood pressure, SBP, and estimated average glucose, E/G. All input values were normalized, using linear division by reference constants, age 70, SBP 140, and E/G 120. The analysis used 16 annual data points, in a three-dimensional space of three variables: age for x-axis, SBP for y-axis, E/G for z-axis, and all distances were calculated using the Euclidean metric. These normalized data points served as three coordinates: x is age, y is SBP, z is E/G, for constructing the TDA manifold, which was also imported into my medical AI software, Chronic, on my iPhone device for numerical calculation, graphic visualization, and extended analysis. In my TDA analysis, during the early phase between from 2010 to 2012, the average pairwise distance among data points was 0.34, reflecting a chaotic and irregular manifold with high variability among variables. In contrast, from 2013 through 2025, the average pairwise distance decreased to 0.09, indicating strong contraction and coherence within the data structure. This represents a 73% reduction in mean distance, showing that my health variables became tightly interconnected over time. As my physiological system stabilized, the persistence diagram revealed one dominant topological feature with a longest bar length of 0.38, representing a single major system transition that occurred during the early recovery, years of from 2010 to 2012. Beyond 2015, no additional persistent clusters were detected, confirming that my system had consolidated into one unified manifold. From a topological perspective, 3 distinct phases were identified. The first phase, from 2010 to 2012, was chaotic, characterized by irregular geometry and metabolic instability. The second phase, from 2013 to 2015, was transitional, showing rapid contraction and improving coherence among variables. The third phase, from 2016 to 2025, represented stable equilibrium, where the manifold became compact and nearly spherical, signifying long-term systemic harmony. In summary, the TDA analysis revealed a single, connected manifold with no structural breaks. The early years were marked by large spatial separations between data points, while the later years showed tight clustering around the center. This topological transformation confirms that my vascular and metabolic systems evolved from instability to stability, aligning perfectly with the trends observed in my VMT energy curve and real clinical data. Finally, I have successfully integrated physics-based modeling, VMT, and mathematical topology, modeling, TDA, into a single coherent framework that unites my biomedical insight with engineering rigor. In this study, the 2 reduction rates observed between from 2010 to 2025, 97% in dynamic energy and vascular damage, VMT, and 73% in geometric shape and systemic order, TDA, provide strong quantitative evidence, supporting my conceptual understanding of both pathology and physiology.